Dear learners, in this presentation, lecture 8, I am going to discuss the concepts of stability. I am happy to inform you that I have made this presentation so short and simple. The learning objectives of this presentation are to understand the importance of stability in control applications, to investigate the stability based on the location of closed loop poles, to understand the necessary and sufficient conditions for stability. Stability means small changes in system input, initial conditions, or in system parameters do not result in large changes in output. For example, let us consider this input. So a 5-volt input is given, a DC input is given. Let us assume that we get an output like this. This is the output that we get. Assume that the initial condition is 0. So here we can find that the output is sinusoidal and it is damped sinusoid in nature, and finally it settles down to 5, that is the desired output of the input. Therefore the system is stable. Now I am changing the magnitude of the input, that is I am making the change in the input, small change, 1 volt change I have made in the input. Suppose I get the output in the same way like the first one, but settling down at 4 volt, because the input is 4 volt, therefore output tracks the input. Again the initial conditions are 0. That means small changes that I have made in the input have not affected the output to a greater extent. Instead of that, if I had got the output like this, here we can find that the output is sinusoidal and the oscillations increase with respect to time. The amplitude of oscillations increase with respect to time. Therefore, the system is unstable. Suppose the output is with initial condition. With the initial condition, the output goes like this, which is oscillatory, and the oscillations increase. There also the system is unstable. Suppose the system starts with initial condition some 2 volt, but later settles down to the input value, the same 5 volt, then also we can say that the system is stable. Therefore small changes in input, initial conditions, even system parameters should not result in large changes in the output. Any practical system is always designed for stable operating region only. Then only it can perform the task for which it is designed. Therefore any control application, any control system is designed only in the stable operating region. So in general, if the output follows the input, we say that the system is stable. There are number of systems: linear time invariant system, linear time variant system, and non-linear systems. Since in classical control we normally take linear time invariant system, we actually refer everything with respect to linear time invariant system. Linear time invariant system is said to be stable if the output is bounded for a bounded input, that is bounded input, bounded output stability. Suppose there is no output, only there is input, but there are some initial conditions. Normally initial conditions we will get due to the energy storing elements. So because of the initial conditions, the output is not 0 initially, but output becomes 0 in the absence of input after some time. Then we say it is asymptotically stable. Generally, if a system, linear time invariant system, is BIBO stable, it automatically satisfies the asymptotic stability. That means we need not check whether it is stable in the absence of input if it is BIBO stable. So let us analyze the BIBO stability. See, the transfer function that is ratio of Laplace transform of output to the Laplace transform of input, is called the transfer function. Let us say G of s represents the closed loop transfer function. Therefore, C of s is R of s into G of s, or C of t is inverse Laplace transformation of G of s, R of s. By convolution principle, we can write C of t as integral 0 to infinity G of tau R of t minus tau d tau. We have seen similar relation even in lecture 7 when we derived the expression for generalized array series. There we use the convolution principle to find out the error series. Now I want to check the BIBO stability. That means I want to take a bounded input and check whether the output is bounded. So I am taking the absolute value or magnitude of the output by this relation. So it is absolute value of this integration. So there is a relation in mathematics. Always absolute value of the integral is less than or equal to integral of absolute value of the integrand. So absolute value of the integration is always less than or equal to integral of the absolute value of the integrand. So here this is the integrand. This is by linearity property can be split up into two components, G of tau modulus R of t minus tau modulus. Let us assume that R of t is bounded. So R of t is bounded means magnitude of R of t is always less than or equal to some magnitude m1 which is less than infinity. Now R of t minus tau means I am time shifting or time delaying this magnitude, or this input R of t by t samples or t time. Therefore this is a shifted version of R of t. R of t minus tau is shifted version. So because of the time shift, the bounded nature of the input is not at all affected. Therefore, if R of t is bounded, modulus of R of t minus tau is also bounded with the same boundedness. Since we have taken modulus of R of t less than or equal to m1 less than infinity, modulus of R of t minus tau is also less than or equal to m1 less than infinity. So this is m1. Therefore, this m1 is taken outside the integration symbol. Therefore, modulus of g of tau d tau is inside the integration. Now, for this output to be bounded, this integration should be absolutely integrable, meaning that integral 0 to infinity modulus of g of tau d tau should be less than or equal to some value. Therefore, m1 multiplied by integral 0 to infinity modulus of g of tau d tau should be less than or equal to m2. That m2 should be less than infinity. That means this integration should be finite. This integration should be finite. That is the meaning. So modulus of R of t less than or equal to m1 less than infinity, and modulus of C of t less than or equal to m2 less than infinity. That is what put here. Fortunately, g of tau, anyway, this here we have taken the time shifted variable. Even we can write this integration modulus of g of t dt also, because just by changing the variable we are not going to affect the value of the integration provided the limits of the integration remain the same. Therefore, g of t is L inverse of g of s. So g of s is the closed loop transfer function. Therefore, inverse Laplace transformation of g of s is going to decide g of t. Fortunately, inverse Laplace transformation of g of s, if we analyze, it is going to be like this. Poles of the transfer function, they are going to decide the behavior of g of t. So this g of t is actually called impulse response, because we have already seen in impulse response R of s is 1, so C of s equal to g of s. Now we are talking about g of t only for C of t. So g of t is impulse response. So impulse response decided by the roots of the denominator polynomial of the transfer function. Therefore, we can see that the location of closed loop poles decides the stability. Let us see how the poles ensure the stability. First, we have taken a transfer function g of s phi by s plus 2. That is, this is the closed loop transfer function. So this has got a pole at minus 2. That means it is having negative real part. So if we find out the inverse Laplace transformation, it is 5 into e power minus 2t. Since the pole is negative real, there is an exponential decay term. Therefore, the exponential decay response g of t will be like this. Therefore, modulus of g of t, integration 0 to infinity, if we find out, this will be bounded only, meaning that the system is stable. Suppose we have pole wherein the transfer function is given by phi by s minus 2, because of that pole is in the right half of s plane. So with positive real. Positive real means when we take the inverse Laplace transformation of g of s, so it is 5 into e power 2t, it is an exponential rise. So here we can find that the impulse response is exponential rise in nature. So if we integrate this g of t dt between 0 and infinity, definitely it is going to be unbounded, therefore system is unstable. Therefore, if the poles are all negative real or they are in the left half of S plane, definitely the system is going to be stable. Even if we have one positive real part or one positive pole in the right half of S plane, the system is going to be unstable. Let us investigate the other location of poles also before coming to the conclusion. So complex poles with negative real part, so minus 1 plus j, minus 1 minus j. So the real part is minus 1, but they are complex in nature. So it is in the left half of S plane. So for the sake of understanding, we have taken a closed loop transfer function wherein s square plus 2s plus 2 is the characteristic polynomial. So if we factorize the characteristic polynomial s square plus 2s plus 2, we will get s plus 1 plus j into s plus 1 minus j. So if we do the partial fraction and then simplify, we will get impulse response as 5 into e power minus t into sin t. So here we can find that we have an exponential decay term as well as sine term. So sine term we have already seen in the second order system response. Always imaginary part of the closed loop poles will decide the oscillations. Real part will decide the exponential rise or decay. This we have seen because in second order system minus zeta omega n plus or minus j omega n root of 1 minus zeta square are the poles. So minus zeta omega n is the real part. So that is what we got, e power minus zeta omega n t, then sine of omega dt we got. So that time itself we have emphasized this. Therefore even when we generalize, when the poles are in the left half of S plane with the complex nature, if the real part are negative, the real parts are negative, definitely the system is going to be a damped sinusoidal only. Therefore finally the impulse response is going to be 0. So if we find this integral g of t dt between the limit 0 to infinity, it is going to be bounded. So system is stable. Suppose we have complex poles with positive real part, that is the poles are present in the right half of S plane. So here 1 and 1 positive real part. So for that I have taken an example, s square minus 2s plus 2, the characteristic polynomial. Of course they have got poles like this. If we simplify by partial fraction and find out the inverse Laplace transformation g of t, it is going to be 5 into e power t sin t, whereas it was 5 into e power minus sin t in the previous case. So here e power t means exponential rise. So sine term multiplied by an exponential rise term. Therefore simple response sinusoidal oscillations will increase with respect to time. Here sine term multiplied by exponential decay term. So oscillations have decreased. So here oscillations have increased. Therefore the impulse response is unbounded because the magnitude increases with respect to the time. Therefore integral 0 to infinity g of t dt modulus is going to be infinity. So it is unstable. Suppose we have single pole at origin. Single pole at origin means the transfer function is 1 by s. So if we take inverse Laplace transformation 1. So here we can find that g of t is simply 1. It is neither decaying nor growing. So if we find the integration, integral 0 to infinity g of t dt, it will be infinity. However, if we do not get the input r of s as 1 by s, that is if the system pole does not match with the input. Real time input is, say, let us step input, it is not step input means, then C of s is simply 1 by s. Suppose system input is 1 by s means C of s would have become 1 by s square. In that case, it is going to be unstable like this. So therefore, we can take this response as marginally stable response. Suppose we have double poles at origin, then 1 by s square. So poles are, poles are at origin and duplicated, multiple poles, and we have s square term. So if we find out g of t, it is t. Therefore, it is going to be linear variation of time. That is, it is going to vary with respect to time linearly. So if we find out the integral 0 to infinity g of t dt, it is unbounded. So impulse response is unbounded, system is unstable. Suppose we have non-repeated poles on the j omega axis, complex poles, but on the j omega axis no real part. For example, we have a transfer function 5 by s square plus 1. So if we factorize this, we will get this poles. So if we find out the inverse Laplace transformation after partial fractioning and simplification, we will get this. So the impulse response will be sinusoidal. That means oscillations neither decay nor grow with respect to time. So like this particular case, if we do not get R of s as some sine input or cosine input, then we will not have sine square term or sine cos term. Therefore, these oscillations, they neither decay nor grow with respect to time. So sustained oscillations. So we can call them marginally stable. Suppose we have repeated poles on the j omega axis. So s square plus 1 whole square. So same thing repeated like this, s square plus 1, s square plus 1 whole square. So if we partial fraction and simplify, we will get g of t like this. So here 2.5 sin t term is not a problem, it will be like this. Whereas minus 2.5 into t cos t means this t, because of this t term, the sinusoidal and cosine oscillations will increase with respect to time. Therefore, g of t is unbounded, the system is unstable. So from these 7 examples, what we can understand is, if all the poles are present in left half of S plane, whether they are real or complex, if they are present in left half of S plane, impulse response is going to be bounded, that is integral 0 to infinity mod g of t dt is less than infinity, therefore the system is stable. If any pole is present in the right half of S plane, definitely impulse response is going to be unbounded, system is unstable. If all the poles are present in the left half of S plane, but for the presence of few poles like this on the imaginary axis but non-repeated, system can be taken as a marginally stable system, provided the system poles do not match with the system input. If any pole is presented in repeated manner, poles are present in the repeated manner on the j omega axis, but remaining poles are present in the left half of S plane, there also impulse response is unbounded, system is unstable. So all these observations are consolidated in this slide. So all roots of characteristic equation, that means poles, negative real part, system is stable. If any root has positive real part, or if there are repeated roots on j omega axis, system is unstable. If this condition 1 is satisfied, but for the presence of one or more repeated roots on the j omega axis, system is limitedly or marginally stable, provided any of the system poles does not match with the input. Now let us understand the classification of stability. So we have understood what is stability, why stability is important, and how to assess the system stability of a linear time invariant system based on the location of poles. Now let us classify stability. So basically there are 3 categories: absolute stability, conditional stability, relative stability. Suppose a system is stable, linear time invariant system is stable for all values of the parameter under the consideration, then it is absolutely stable. For example, let us consider the characteristic equation s square plus ks plus 2 equal to 0. Here whatever be the value of k, if k is greater than 0, definitely for all values of k greater than 0, that is the gain greater than 0, system is going to be stable. So here conditional stability, next classification. So conditional stability means if it is stable only for certain values of the parameter or certain range of values of parameters, bounded ranges of values of parameter, system is stable. So there is some condition with respect to the stability. For example, we consider a characteristic equation like this: s cube plus 2s square plus ks plus 5 equal to 0. So this particular system is stable only when the parameter k is greater than 2.5. So when k is less than 2.5, the system is unstable. Then the relative stability. So relative means we are comparing the stability of two systems. So it actually gives the measurement of how fast the system transients die out. So how fast the system actually goes to the steady state. So it gives the degree of stability. So to what extent the system is stable. So the degree of stability is measured by the relative settling times of each root of pair of roots. That means we find the settling times of dominant roots, which we have already seen while we discussed the time response of second order system in lecture 6. So dominant roots are the roots which are the closer to the j omega axis in the left half of S plane, because they are going to dominate the performance of the system. So if a root or pair of roots move away from j omega axis in left half of S plane, relative stability of the system improves. For example, let us consider system A and system B. So here the dominant roots are at -3 plus j minus 3 minus j. Here the dominant roots are -1 plus j minus 1 minus j. Let us forget about the other two poles, because anyway they are in left half of S plane. So only these two poles for this system and these two poles for this system are going to decide the stability. They are going to dominate the behavior of both the system respectively. So here these dominant poles are more negative real than this. Or if we use this particular concept, relative settling time, here the settling time is zeta omega n minus zeta omega n plus or minus j omega n root of 1 minus zeta square are the second order poles. So settling time is inversely proportional to 3. Here settling time is inversely proportional to 1. Therefore this settling time is definitely less than this. Therefore system A settles down faster than system B, or I can say transients die out in system A faster than the transients in system B. Therefore system A is more stable than system B. So that is what the exact meaning of relative stability. Now let us understand the necessary and sufficient conditions for stability. Just by seeing the characteristic equation, how can we come to a conclusion on system stability? So what are the necessary and sufficient conditions for the same? For example, let us consider a first order system with the characteristic equation a0 s plus a1 equal to 0. So the coefficients are real, a0 and a1 are real. So if we find out the poles, minus a1 by a0. So if both a0 and a1 are positive or both are negative, this s is going to be negative. If s is negative means the pole is negative, that means pole negative real means definitely the system is stable, because we have understood in the location of poles in the S plane for stability. If any coefficient is negative, for example a1 is negative or a0 is negative, meaning that this s is going to be positive. If the pole is positive, if you have a positive real part for the characteristic equation, definitely the system is going to be unstable. Suppose the coefficient a1 is missing, a0 cannot be missing. If a0 is missing, it is going to be zeroth order system. Since we are considering first order system, we have to see what will happen when a1 is 0. If a1 is 0, a0 s is equal to 0. That means pole is at origin. If pole is at origin means the system can be marginally stable. This again we have understood in the location of poles in S plane for stability. For example, let us consider the characteristic equation a0 a square plus a1s plus at equal to 0, which is a second order system. Let us assume that all the coefficients are real. So the poles, if we factorize this using, if we find out the roots using the quadratic equation formula, so minus a1 plus or minus square root of a1 square minus 4a0 to a0 a2 divided by 2a0. Suppose all a0 a1 a2 are positive means definitely 4a0 a2, that is a1 square minus 4a0 a2 will be definitely less than this particular, inside the square root will be less than a1 only. For example, let us assume a0 a1 a2 as 1. Therefore minus 1 plus or minus root of 1 minus 4. So 1 minus 4 is minus 3. So root of minus 3 by 2. So minus 1 plus or minus root of minus 3 by 2. That means minus 1 plus or minus j root 3 by 2. So minus 1 plus j root 3 by 2 minus 1 minus j root 3 by 2. So both have negative real part. Both are complex and negative real part. System is stable. Suppose one of the coefficient happens to be negative. A1 is, for example, let us say A1 is negative. So A1 is minus 1, A0, A2 are 1. So minus A1 would have become plus 1. So here A1 square minus 4 A0 is, so again 1 minus 4 A0 A2. So 1 minus 4 is minus 3 root 3. So it is square root of minus 3, that is j root 3 divided by 2. So 1 plus or minus square root of j root 3 by 2. So 1 means positive real. So positive real means system is unstable. Suppose a coefficient A1 or A2 is missing. For example, A1 is missing means A0 s square plus A2 equal to 0, or A0 s square is minus A2, or s square is minus A2 by A0, or s is equal to plus or minus j into root of A2 by A0. That means non-repeated roots on j omega axis. That means system is marginally stable. Suppose A2 is missing means A0 s square plus A1 is equal to 0. In that case, if we take s as outside, s into A0 s plus A1 equal to 0. So s is equal to 0 is one pole is minus A1 by A0. So s is equal to 0 means one pole at origin, therefore system is marginally stable. So in both the first order and second order system, what we can understand is, if all the coefficients are positive and real and none of the coefficients missing, system is stable. If any coefficient is negative, system is unstable. If any coefficient is missing, system is at the most marginally or limitedly stable. Let us see a third order system with the characteristic equation s cube plus s square plus 2s plus 8 equal to 0. So in this particular case, if you find out the poles, these are the poles: minus 2, 0.5 plus j root 15 by 2, 0.5 minus j root 15 by 2. So here the real root happens to be negative, whereas the real part of the complex roots happen to be positive. So even though all the coefficients are positive, like first and second order system, the system is not stable. Therefore, positiveness of the coefficients of the characteristic equation is not necessary or not sufficient to ensure the system stability. Therefore, positiveness of the coefficient of the characteristic equation ensures the negativeness of real root, but does not ensure the negativeness of real parts of the complex roots for third and higher order system. Therefore, positiveness of the coefficients is only a necessary condition, it is not a sufficient condition. Therefore, how to check the system stability for higher order system, third and higher order system, means we cannot go by solving the roots, because solving the roots we don't have readily available mathematical tools. So it is tedious and time consuming procedure when we go for a third and higher order systems. Therefore, we should have some tools to solve that. So that will be Routh and Hurwitz's criteria that we will discuss in the next lecture, lecture 9. Thank you.